The most accurate XGBoost trial may be too slow to ship. Optuna's Pareto front exposes the accuracy-latency trade-off, so you can choose a model that meets both. After this, you'll understand how to assemble a pipeline that compares quality and speed, shows the trade-off, and picks a deployable model. I'm Professor Pi, teaching AI foundations with simple Python. Start with the practical problem. You want a model that scores well and responds fast in production. Many tuning guides chase one metric and ignore serving cost, and that often leaves you with a model you can't actually deploy under your latency target. Multi-objective tuning fixes that by treating accuracy and inference time as two things to optimize together. The intuitive idea is straightforward. We will train XGBoost models while tracking two numbers: validation AUC for predictive quality and average inference time on the validation batch as a proxy for serving latency. Optuna will explore many configurations and return a Pareto front, the set of models that aren't dominated on both metrics. From that front, you pick the model that best balances quality and speed for your SLA. We will build a small, reproducible pipeline that creates a fixed validation set, trains a baseline XGBoost, measures latency, runs an Optuna study that returns AUC and latency, and finally picks a trial from the Pareto front that meets a simple latency cutoff. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. To begin, we need a single fixed validation split so every trial is judged on the same scoreboard. This snippet creates the small validation setup every tuning run will share. If the split keeps changing, you cannot tell whether a better score came from a better XGBoost configuration or just a friendlier validation sample. Scikit-learn make classification gives us an interpretable binary classification dataset. And train test split holds back 25% for validation. The stratify equals X argument keeps the class balance similar across train and validation, which makes AUC comparisons less jumpy. The visible output confirms the two row counts, so the rest of the tutorial has one fixed scoreboard. Now that the data is stable, we train a single baseline XGBoost to see the quality before we consider speed. This example trains one XGBoost baseline before we start searching. A single metric tuner would often stop here. Fit XGB classifier, call predict proba, and reward the model with the highest ROC-AUC score. That is useful, but it ignores whether the model is fast enough to serve. XGB-args keeps shared XGBoost settings in one place, including njobs equals 1, so later latency measurements were easier to compare on the same machine. The printed validation AUC gives us the quality side of the trade-off before we add speed. Seeing accuracy is helpful, but it hides the cost of predicting at scale. Next, we measure how long a validation prediction actually takes. This code measures the speed cost that plain AUC tuning hides. Latency MS uses time.perf counter around repeated predict proba calls, then reports average milliseconds per validation batch. Repeating the call smooths out some one-off timing noise, but it is still a local measurement, not a universal benchmark. Increasing repeats usually makes the number steadier, while decreasing it makes the snippet faster to run during experimentation. The printed baseline latency MS gives the speed side of the same model we already scored for quality. With quality and a baseline latency in hand, we are ready to let Optuna search for configurations that trade those two goals off against each other. This snippet turns the trade-off into an Optuna study instead of a handwritten compromise. The objective builds an XGB classifier from trial suggestions, fits it, then returns two values: validation AUC to maximize and latency MS to minimize. Optuna create study receives directions in the same order as the returned tuple, so the meaning stays explicit. More N trials gives Optuna more chances to find useful trade-offs, but it also trains more XGBoost models. The visible output confirms the study actually evaluated the requested number of trials. After Optuna finishes, you do not want a single best trial. You want the Pareto front and a sensible pick for deployment. This example uses Optuna's Pareto front instead of pretending one score tells the whole story. Study Best Trials contains trials that are not clearly beaten on both AUC and latency. So front is the set worth discussing. The limit MS line creates a simple latency cutoff from the middle of that front, and chosen picks the highest AUC trial that stays under it. Plot Pareto_front study builds the visual trade-off chart you would display in a notebook or dashboard. The printed chosen trial, AUC, and latency MS show the final deployable choice, not just the most accurate model. If you move this toy flow to a real project, map the validation batch size, and predict repetition to your real request size and concurrency. Measure latency on the same hardware you plan to serve on, and use the same input pipeline. That alignment keeps the Pareto choices meaningful when you go to production. 3 quick points to remember. Multi-objective tuning optimizes quality and speed together, not separately. Use it when inference latency matters for user experience or cost. One caveat is that measured latency is local and can change with hardware, batch size, or server load. A strong next step is to run the same pipeline on your production dataset and tune XGBoost, max depth, and N estimators while targeting a specific millisecond SLA for latency. That will show you concrete trade-offs and a deployable model for your service. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.